Good day, welcome to this video. In this video I'm going to be showing you how to code a delay subroutine in the PIC18 microcontroller, specifically the PIC18 F45K22 microcontroller. And yeah, so before I start the code, there are some settings to be made. In this particular tutorial, I won't be showing the results in Proteus because MPLAB actually has a better way of showing your delay using the stopwatch function. So I'm just going to show you how to open up the stopwatch and configure it. So you go to Window, Debugging, and Stopwatch, and there's your stopwatch over there. And secondly, to configure the stopwatch, the instruction frequency rather. So you have to go to project properties. Yes, project properties, and in essentially what you're doing in project properties, the reason I opened the project properties is to change the instruction frequency, and that's important for the stopwatch functionality. And so you go to the simulator, and right over here where it says instruction frequency, you have to ensure that the value here is 4 times less than your oscillator frequency that you've chosen in your code. In this particular example, the oscillator frequency I chose was 4 megahertz. So in this case was 4 megahertz. So in this case, the instruction frequency would actually be 1 megahertz. Okay, so let's say your oscillator frequency is 1 megahertz. This would be 250 kilohertz. You would just make that 250 kilohertz. Yeah, but if it was like in this case, the oscillator's 4 megahertz, so I'm just going to leave it as 1 megahertz over there, and that's that. So I just apply that, and okay. Yeah, and that's that for, and that's how you configure your how do you say it, the stopwatch. And now down here and down there, you can see the instruction frequency is 1 megahertz. And now I'm just gonna get into the code. And now essentially the same, it's the same format, the coding format. So you start with the title, the list, and the configuration bits. And the configuration bits you essentially do by going to Windows, target memory views, configuration bits, and here for the frequency of the oscillator you just select int IO67. That basically you're indicating that you're going to be using the internal oscillator, not an external one. And next you go to the watchdog timer. That should be off. So watchdog timer is off. Okay, I think I should make this bigger. And next, the low MCLRE, ensure that it's ext MCLR, so that essentially enables the MCLR pin. And the final one is the low voltage programming. That should be on, which it is by default. And you go down here, you generate source code to output, and what you do is you copy it, and yeah, copy it, and you paste it, right over here. I already did that, so I'm not gonna do it again. So yeah, that's the configuration bit. And next you have to create variables. So essentially what the C block does, it helps you create variables. So this is how you make the C block, almost like the C++ equivalent for that is probably something like int delay variable 1, and I have 5 delay variables here. So this is the C block. And next you just start the code by using this command, and then in essence just tells you code where it's the starting point. And here the starting point of the code is initialization. And over here in the initialization, I initialize the oscillator to be 4 megahertz, and I'm using in this example port RA2. So let me go to the oscillator initialization. So this is how you initialize the oscillator to be 4 megahertz. You have to set to the 6th bit. This is the 6th bit. You have to clear the 5th bit. This is the 5th bit, and you have to set the 4th bit. And this is how you set the 4th bit of the OSCON register, and that gives you 4 megahertz. And yeah, and the port init, essentially for this particular example, we're using port RA2, and that's how you do that. So first off, you have to disable analog functionality of the pin, and this is how you do that. So if this was RA1, this particular bit would be 1 instead of 2. But we're using RA2 in this example, so that's 2. So you disable the analog functionality of RA2, and then you make RA2 an output by clearing the RA2 bit of the trace A register. And that's how that's done. And then afterwards, we go into the main function. There, we set the RA2 bit, make a delay, and then you clear the particular bit, and that's it. And that's how you do that. And that's how we did. That's how it is in this example. And essentially, honestly, these 2 lines, this BSF up here and this BCF, I just created those to essentially for breakpoints. In essence, they're actually not needed. I just needed a spot to break to, well, test the delay, and also to check the delay using the stopwatch, right? You need breakpoints. You need breakpoints here and here. And usually once you debug, the code is gonna stop at the first breakpoint, and then when you press the play button and the panel, that's gonna show up here. Once you press the play button, then it will jump to this next code, and then the amount of time it took is gonna show up in the stopwatch over here. It's gonna show up right over here, and that's how you do delay. So I'm just gonna get into this now. And with regards to delay loops, the code is quite boring for it, because it usually stays the same. So this is for 3 loops. This is the code for 3 loops. So for delay loops in the PIC microcontroller, you're essentially just wasting time by executing a loop a certain number of times, and usually that number of times is not enough. You execute another loop outside of that for a certain amount of time. If that's not enough for a time delay, you execute an outer loop after that, another loop, etc. So for this particular example, I'm gonna only execute 3 loops maximum. So this is a 500 millisecond delay, and so I guess the tricky part for delay loops comes where you have to determine the values to plug into each register, which is the essence of this video. So to do that, there's a formula that's used for that, which I'm gonna show you now. Just open it up. Okay, so that's the so this is the formula you usually use for delay loops. So this is in essence means time delay in seconds is equals to 3xyz plus 5yz plus z 7z, all multiplied by 4 divided by the frequency of the oscillator. So x represents the value for the outer loop, y represents the value for the middle loop, and z represents the value for the inner loop. And these are registers, by the way. So in that particular example in the MPLAB, the z is delay variable 1, I think. Let me just confirm that. Yes, z is delay variable 1, y is delay variable 2, and x is delay variable 3. And the max values for all these registers is 255. And yeah, so what I usually do, so this right here that I'm highlighting, I hope you can see that I highlighted that. Yeah, so that part that I just highlighted, that's how you calculate the value for the outer loop. So the trick is essentially you have to guess the middle loop and the inner loop values. You have to guess them. There's no way around it, honestly. You just guess them, and once you guess them, then you calculate the value for the outer loop. Usually, to simplify it for myself, I usually just guess the same value for the y and the z. So in this particular case, I guess the value of 40. So if you guess a value of 40 for y and z, which is the middle and inner loop register values, the outer loop will become 100, and when I punch that into the calculator, I get 102.44. That's the value I get. So I'll just go back to the code. And keep in mind the TD value for this particular example, you have to use 0.5. Please don't make the mistake of putting 500 there. The TD is in seconds, not in milliseconds, so that's something you have to watch out for. So the TD is going to be 0.5 in this particular example, and the X value you get is 102.44. So I'm just going to go back to MPLAB now. As you can see here, the values I've put in here. So this is for the middle loop, it's 40, the inner loop 40, and the outer loop is 101. Well, it's not 102 because I checked before I started recording this video, and 102 actually gave me a delay of about 506 milliseconds. So, but 101 gave me a much favorable value, which was 501 milliseconds. It was much closer to the desired value. So that's one thing to take note of, and that in essence is a 3-loop delay loop, and that's all you have to do. And to test it, you just do that. You debug, and it's gonna stop here, and then it's gonna press the play button, and it's gonna jump to the next one. Before I do that, I just want to explain the 2-loop delay, the 2-loop version, and this is the 2-loop one. And usually what determines whether you use a 3-loop or a 2-loop to execute a delay loop is essentially just the amount of time you actually need. So what I usually use is if I need a delay greater than 150 milliseconds, then I use 3 loops. If it's lower than 150 milliseconds, I use 2 loops for 4 megahertz. So that's how I determine how many loops I'm gonna require. Keep in mind, if you want a delay of less than 150 milliseconds, you could use 3 loops for that. Just keep in mind that your accuracy is going to be really off. It's going to be, it's not going to be great, your accuracy levels, with regards to the delays, right? So you might change a register. So what I mean is, essentially, you could change a register, like in this case, you see 200 there. If it was 3 loops, you could, if you changed it to 201, right, your delay could jump from your delay could jump by actually 10 milliseconds, right? So that's not great resolution. That's not a great resolution. So you want to use a 2 delay loop if it's less than 150 milliseconds, and greater than that, 3 delay loops is usually better, honestly. So this is essentially a 2 delay loop. It's not so different from the 3 loop one. It's just 2 loops, and there's an inner loop and an outer loop, and the formula is also different. So let me just show you the formula for this particular one quickly. Okay, so no, this is for 3 loops. Let me take it back to 2 loops. So as you can see in this particular formula, the time delay in seconds also is equals to 3xy plus 5y, all multiplied by 4 divided by the frequency of the oscillator. So in this case you only have to guess one value, which is nice. So in this case initially I guessed the value of 50, but you'd notice, and the frequency of the oscillator is 4 megahertz. So yeah, I guessed the value of 50 initially for y, which is the inner loop value. And if you calculate that, and sorry to cut myself off so quickly, the time delay for this that I'm trying to get is 120 milliseconds. So yeah, there's 120 milliseconds. So the TD is gonna be 0.12. So back to it. So initially I chose a y value of 50. So if you punch that into your calculator, you will actually notice that the value that you get is 798, which is a lot more than 255. So what you must do is you must increase the y value by 50 just to get the x value below 255. So if you choose a y value of 100, it's 398. It's still bigger. So if you go to 150, it's still bigger. It's 265. So you go to 200, and now it's 198.33. And obviously the microcontroller does not understand floating point values, so you're gonna have to well, it understands floating point, but not in that form in assembly anyway. So you have to take that down to 198. It's just gonna go back to the code, and as you can see, the value for delay variable 4, which is the inner loop, is 200, and we guessed that value. Well, I guessed that value. And for delay variable 5, which is the outer loop, it's 198. That value was calculated using that formula, and you would find that this delay is actually 100, and when I checked it out, it was 119.598. But I will show you guys, don't take my word for it. I will show you that that's the actual delay that I got. And also, just before I move on, if let's say you calculated for 120 milliseconds, and you realize, oh wait, I actually want 100 millisecond delay. I don't want 120. Instead of going back to the formula, you could just scale this, right? You could scale this value here. So all you have to do is you just have to take one of the register values, 198 or 200. In this case, I'm going to take 200. So you're going to say 200 multiplied by 100 divided by 120. And that will give you a value of 166.67. So if you replace the 200 with 167, you would get a time delay of 100 milliseconds. So that's just for those of you that don't want to use the formula all the time. You could do that. And also there's another way to do delay loops without using the formulas. You could just you could literally just guess the two values and just go from there and use your stopwatch and increase, reduce accordingly. The problem with that, it takes time, and in certain situations you don't want to spend too much time on delay loops, if you know what I'm saying. You want to get through it pretty quickly and carry on with the rest of your code. So in those situations, a formula is important. It's important to have a formula to use where you can just plug in and it's bankable. It works most of the time. Well, I say most of the time, it works all the time. It's just sometimes it's a little bit off, so you might have to decrease one of the register values to just make it, bang on or closer to the actual delay you want. So I'm gonna show you what I'm talking about just now. And yeah, so I'm just gonna run the code first off for the 500 millisecond delay, and then after that I'm gonna run it for the 120 milliseconds delay. So as you can see here, it's 101. So before I do that, remember I calculated 102.44. So let me just make 102 and show you what we get for that before I change it back. So debug. I'm just waiting for and yeah, so it stopped there. It stopped at the breakpoint. So now I'm just gonna go to stopwatch on the stopwatch tab, delete, and play. Press the play button, and I hope you can see that the delay is actually 506.334, which is a little bit over, well, relatively a little bit, but it's over. It's not 500 milliseconds. It's not the desired value. So what you do is you just go down back there and just decrease that by 1, or you could decrease the 40, any of the 40s to 39. I just prefer to decrease the outer loop because it makes more sense for me to do that. And you save and you debug again. And so go back to stopwatch, delete, and that's much closer. So that's 501.37 milliseconds, and that's a lot closer to 500 milliseconds. And you might be wondering, like, this is not so accurate. It's not bang on 500 milliseconds, but it's not right on it. So if you wanted a more accurate delay, you're gonna have to use timers. I'm not gonna be touching on that in this video. Probably another video I'll touch on using timers, how to use timers for your delay. But this but for like a quick delay loops are really helpful for that. And as long as you have a formula to do that, the code essentially stays the same, just the values in it which you use the formulas for. That's how they differ. And yeah, that's delay loops. And yeah, so you get a 501.37 milliseconds delay from this. And now I'm gonna check for 120 milliseconds. I'm just gonna close that, save, and run. Okay, it's ready. Just gonna go back to stopwatch, delete, and play. As you can see there, it's 119.598 milliseconds. You see, this is much more accurate. So the less the amount of delay loops you have, the more accurate you could get them. You could get the values. And yeah, that's for 2 delay loops. And remember I said for 100 milliseconds you would scale this code and you'd make this 167, and just change that to 167 and just show that and run. And you go to the stopwatch, delete, and yeah, that's 99.996 milliseconds. And yeah, so that's delay loops, guys. There isn't much more to it. Essentially, the formula is just, I'm sure some of you might be familiar with delay loops. This video is essentially just to show you a formula to make it much quicker to perform the delay loops. That's quite ironic, quick, considering this video is, almost 30 minutes long. But yeah, so that's how you do delay loops to be more bankable and quick. And just if you wanted to use this code for a blink, you would have to uncomment this line and comment out this line, uncomment this line, and then it will turn on the LED, make a delay, turn it off, another delay, and etc. It won't stay like that in a loop. And yeah, but that's not this example, so yeah, just change that back to the way it was. And that's delay loops. That's it. And let me just go back and change it to the normal value for 120 milliseconds delay, 200, and that's a delay loop. Okay guys, that's the end of the video. Hope this was helpful for you, and that's it. I hope wishing you best of luck with delay loops, coding it, and thanks for watching.